Hello, everybody. My name is Alexey Bekin. I'm DevTech engineer with NVIDIA. And now today's topic is neural shading, practical techniques and applications.
Remind them to silence the phones.
Yeah, please silence your phones. Thank you. So it will be three-part presentation. So I start with neural shading, then Alexey Panteleev continues with neural texture compression, and then Sean explain hardware implementation for some hardware extension we use. So what is our goal in neural shading? So on the screen you can see two spheres. And first one is actually shaded with a Disney shader, just standard one, and the second one on the right is its neural approximation. This is a screenshot from our SDK, so that's how it looks like after some training. So first of all, neural shading SDK is a part of NVIDIA RTX kit that was released recently, and it includes just 4 samples. We're trying to organize those samples so it would be like going from easy part to more complex topics. So first sample is about inference of pre-trained model neural shading. Second one is about texture training using backpropagation algorithm. Then Disney shader training using Slang autodiff. And we also have Python interface for Slang Py, and we have a sample for that. We have some libraries that make it easy to work with neural nets and Slang and Cooperative vector extension that we use. So here is again screenshot from shader training example from our SDK. So on the left is original Disney shader. In the center, it's neural shader that approximate Disney shader. And you probably can see that there is a differences because it's just 3 seconds into training on RTX 4090. And on the right, there is a color difference for different components of that shader, and you can see there is a significant difference at that point. And after 20 seconds, it's almost identical. So they look exactly the same. So about what is behind the scene. So we use neural network that is multi-layer perceptron, MLP, that is fully connected. And on the left side, green circles represent input. On the right, blue ones represent output. And we have, in this particular case, 2 hidden layers with pink circles. So everything is fully connected. So every layer connected to every node connected to all nodes on the previous and next layer. And every connection is associated with a weight, and at the output of every layer we have some bias value. So on the top there is an equation that shows how we transform values from previous layer to the next. And it's basically a matrix multiplication between weight matrix and input from previous layer plus bias, and after that we apply some activation function, which should be nonlinear for this to work. So how we can apply that to shading problems? So typically for pixel shader we have some inputs of the described lights, camera position, view direction, some material parameters. So we can concatenate all those values in the input layer of the network. And at the end, we would like to have RGB value, like we have in pixel shader typically. So training would like this. So we have input, we produce some RGB value as an output of the network, and we have some original RGB that we already know. So we compare them, and we need to alter all those network parameters somehow to improve result of this RGB value that's coming out of the neural network. So we organize it. So here is a chart how we do that. We have input parameters. We put those input parameters the same way to the input of the input pixel shader, in this case, Disney pixel shader, and to the input of MLP. And they accept the same inputs and produce the same outputs. And we put those two outputs from pixel shader and MLP into loss function, which should produce just one discrete value describes how close results from pixel shader and MLP. Using that value, we should calculate a gradient for loss function. And then we use that gradient to put that gradient in the optimization part that actually may make that correction to MLP parameters. Training itself is, in machine learning, typically organized in epochs and batches. So in this particular case, what happens, we generate input parameters set that consists, and then we have a batch that consists of multiple those input parameter sets, and at the end, every input parameter set produce a separate gradient. So at the end, we should average all those gradients, and at the end of epoch, we actually run optimization part and do correction for MLP internal parameters. So algorithm we use and consider is backpropagation algorithm. So on the right, we have some equations that describe transition to the next layer from previous. Again, it's just matrix multiplication to the input of the layer plus bias, and after that, activation function is applied. In backpropagation algorithm, we should separate the transition into two parts. The first is linear part, and second one is activation function. So we define delta LG as a partial derivative of loss function by that linear part vector components. So in that case, backpropagation equation can be written in those two parts. And what we actually interested in, those partial derivatives of loss function by biases and weights. We need actually a partial derivative for all biases and weights to do optimization. So on the left, algorithm is described. So we started with some input. We do feed forward, where we compute those linear parts and apply activation functions. And at the end, we calculate output error, which is per component multiplication between derivative of activation function for the last layer and gradient of loss function by output of the last layer. Then we use that error to compute some derivatives for both weights and biases. And then we do next step back. We compute error for the previous layer, and we continue that. That's why it's called backpropagation, because we're moving from the back to front of the neural network. Now we connect this equation with the actual code. And here we use Cooperative vector extension. Currently, those extensions implement as a Vulkan NVIDIA extension, vendor specific. and currently it will be, so in current state of SDK, but very soon it will be a direct version for that, and we will update SDK at that moment, so it will be available in DirectX as well. But for now, we have those functions to implement different steps of the backpropagation algorithm. So first you can see, it's actually code, Slang code from SDK, where you can see that we define linear operation and a little bit about parameters. So we have cooperative vector parameter IP, and we have a structured buffer where we store all weights and biases. We have offset for weights and biases to accept them, and we define matrix layout. Actually, there are multiple layouts possible in vector cooperative extension. Typically, we use inference optimal and training optimal correspondingly. So for training, we use training optimal. But also there is a row major layout where we, just to exchange data between GPU and CPU. And there are commands to do conversion between those different layouts on GPU side. So this is just one part of it, and there is just 3 commands from cooperative vector extension that actually implement those 3 steps in backpropagation algorithm. So first one is outer product accumulate, and remember what I was saying about how we do training. We do that in batches, so we should accumulate all those gradient values. That's why those 2 functions actually name ends with accumulate, because they at the end of calculation they do atomic accumulation for gradient components. So first one is produce partial derivatives for weights, and second one produce those. It just actually atomically accumulate those values. We already have them, and at the end we have functions that implement this matrix multiplication to produce errors for the next step. For the input, additionally, for linear operation backward function, we have read-write structured buffer where we actually put all calculated values of this gradient of loss function. So here is a Adam optimizer that we use, and practically in our implementation we do training and FP16 precision, but optimizer step actually use mixed precision, so it stores some gradients for making steps from one epoch to another. It stores it in float point 32 bits, so it's mixed precision implementation. And another optimizer, we have just 2 moments and some unbiased corrections, and in the end we have a transition from one set of parameters of the neural network to another using learning rate with new and some additional small numbers. So it's all part of the Adam optimizer. So again, it's that step is run on GPU as well. So backpropagation algorithm is only applicable for just fully connected neural network. So if you want to do something more complex, like connect 2 MLPs with some additional input, or we want to implement something like recurrent MLPs, when we put some output, we use some output as an input for the next run of the neural network, we need to change that algorithm. And actually, if we experiment, and it's very hard to implement that algorithm every time we change configuration of the neural network. That's where actually Slang is very helpful, because it has automatic differentiation built in. So if you can redefine that step between different layers as a function, we can express the whole loss function in this form when we have y as the known values to which we compare, and we have nested calls of function f for different layers. And using chain rule for differentiation, we actually can express partial derivatives of loss function for any layers through the chain of partial derivatives from right, where it's partial derivative of loss function by output of the last layer, and then multiplied by derivative of last layer by values from previous layer, and so on, until we reach the first layer of the neural network. So how we do that in the code? So here is again chain rule, and here the interface in Slang, how we define actually activation function. So activation function, it has template parameters t, which means just a type, and size k. And we have just one function in that interface. It's actually evaluation of that function, but you can see that there is a keyword differentiable. That means that Slang will try to, if it's asked to do, it will try to automatically calculate a derivative for that function. So below that, it's just very simple activation function that implement that interface, and it's defined just as an exponent. Exponent is built-in function, so Slang knows how to calculate exponent, but it doesn't know how to calculate derivative of exponent, so we need to define it. And we define it in form when we put keyword backward derivative and we point it to original function exponent. And now we define how to calculate derivative in this case. So instead of just cooperative vector input parameter, we now have differential pair. So that differential pair type stores both original value in form of cooperative vector and derivative of those values for this specific function. And you can see second parameter is actually what coming from the right side of the chain rule. So first we just pass 1, and after every step it should pass that previous values from the right side of the chain. But it's all done automatically by Slang. So you can see we just form a pair where we put that original value and we just multiply that right side by exponent, because exponent derivative is itself. So it's a simple case. But what it gives us, you can see on the right, where we define two additional activation functions, swish and hyperbolicity tangent function. And they define it just as some arithmetic operation plus exponent. And we again declare them with keyword differentiable, but now we don't have to define any derivative for this function, because Slang knows how to calculate derivative. It knows how to calculate derivative for arithmetic operation, and plus we define it derivative for exponents. So now it has all components to do that calculation automatically. Now about derivatives autodiff for linear part. Actually, we can define the same linear operation just in a little bit different form. But now we define that backpropagation step, so linear backpropagation, as a backward derivative for linear operation. What it actually is, it's actually calculate those derivatives. So now we have differential pair as an input, and we have differential PTR pair. That actually where we store our buffers, because we calculate derivatives by parameters of the network and they are stored in the buffer. So again, we return just differential pair of original input and result of backward step. So a little bit about how we define storage for derivatives that we calculate automatically. So you can see this is how it's done in Slang. So we have structure that stores just structured buffer. And it's read-only buffer because we don't change derivative when we train. And we define, so you can see that the type alias differential, and it points to another type where we store those derivatives. And now it's read-write structured buffer because we write derivatives to that buffer. And again, we declare it as a this differential type alias. So Slang can recognize it as a storage for derivatives. So we put it all together. So this is a piece of code from MLP implementation. So you can see there is two functions, forward and backward. Unfortunately, Slang currently cannot do autodiff for member function. That's why we separated that forward underscore s function as a static. And we declare it differentiable. Now it has input like input parameters, the storage for parameters of the network, array of the offsets for weights and biases, and to activation function we use the same activation function for transition between all layers except final layer, and we have that final activation separate. And now there is a code, there's a linear operation that applied to the input, and we apply activation function, then we have unrolled for loop where we do the same until at the end we apply final activation function to the output of the last layer. Now we have all components defined. Now we have derivatives defined for linear operation. We have derivatives defined for all activation function. And now to do backward step, we just need to call the specific keyword bwd underscore diff. And we just asking here Slang to calculate derivative automatically for forward underscore s function. And because it's currently knows all components, we define everything, it can do that automatically. So some training tips for neural shading. First of all, it's very important to reduce number of input parameters of MLP because the number of parameters we need to show to MLP for train, it grows exponentially with the number of input parameters. We need to normalize MLP input values so with some range. In our case, it's dot products, so they naturally normalize to 0 to 1. We use encoding to accelerate MLP training. I will show how to do that in the next slide. We apply weights. It's a form of normalization of MLP output because output of the network for different parameters can be different scales, so we need to apply some weights to put them into the same range. And we use reduced precision where possible, so in training we use FP16. In optimization, we use both 16 and 32, and of course use hardware extension because they use internal hardware specific for machine learning. In case of NVIDIA, it's tensor cores. So frequency encoding, it's just technique when we replace every component with some values of sine and cosine with p multiplied that parameter and multiplied by power of 2. So in our case, we use 3, so instead we produce 6 times more inputs for neural network to optimize training. And here is a chart for all shaders that we use in training and in inference. So on the left, we have original Disney shader that separated into 3 parts. First is extract input parameters. What we do, we just produce dot products from view, light, vectors and some material parameters. Disney core part where it calculates diffuse, some specular, clear code components, and finally color calculation where GB value is produced, and similar scheme is used for inference pixel shader, where again we use the same input parameters encoded the same way, so they just calculate dot products. All those dot products goes to neural network, and it produces the same components, diffuse, specular, so on, and color calculated exactly the same way. And training compute shader, we use input parameters that are generated using just random generator. We run the same code for Disney shader, for MLP, calculate loss function, accumulate gradient values, and do optimization at the end in a separate compute shader. And this is it for my part. Thank you very much. Felix.
Thank you. So I am Alexey Panteleev, and I work mostly on the Neural Texture Compression SDK, which is what I will be talking about here today. But first of all, before I talk about Neural Texture Compression itself, I would like to give you kind of an introduction to how, that will help you understand how Neural Texture Compression works. And let's make this kind of a mental experiment or toy experiment by looking at the BC compression, and such as BC7 mode 6. BC compression, it's a pretty old standard, and it's supported by all the current GPUs, but the core idea here is that we take the image or texture and split it into blocks of 4x4 pixels, and for each block we have one or multiple pairs of endpoints. And the colors in the block are interpolated between the endpoints. So for simplicity, let's consider just BC7 mode 6, which has one pair of endpoints for the entire block, and some weights that interpolate between these endpoints to get the colors for the individual texels. So for the block, we store one endpoint, the other endpoint in color space, and 16 weights for interpolation. So this BC7 compression can be framed as a machine learning or optimization problem. How's that? We started by implementing a BC decompressor, giving the endpoints and the weights, we convert them into the original colors. That's our kind of inference function. Then we implement a loss function that compares the output of the inference function or decompressor with the reference, which is the original colors from the texture. And then we can take that loss and backpropagate it through the decompressor and apply optimization like gradient descent to gradually, step by step, converge onto the right or optimal answers for the endpoints and the interpolation coefficients. It will take some time, and I should note that while this will actually work for BC7 mode 6, don't really use it for BC7 because this problem of BC compression, it's simple enough that machine learning is not necessary here. It's just easy to understand. There are easier ways to deal with BC compression. So now on to neural texture compression itself, and it's based on this paper from 2023 that I've mentioned a number of times already. And based on the paper, we have created an SDK called RTX NTC for neural texture compression. That SDK is now available, and it has 4 main components. One shown on top is libntc for the library that has 2 subsystems, one with CUDA compression and decompression. It's mostly historically CUDA because when the work on the SDK has started, the cooperative vector extensions didn't exist yet. And there is a kind of runtime subsystem that works in Vulkan and DX12 that is designed for use in games and engines, that does inference on load and transcoding into BC, and also inference on sample. It comes with 3 tools: the command line tool that is designed for kind of offline or just processing of textures, NTC compression in like asset preparation pipelines and such, and also decompression. NTC Explorer, which is a tool that lets you visually inspect the compression results and compare like inputs to outputs, compare the runs to each other. And if time permits, I can try to show a demo of it today. And finally, the rendering sample that shows the inference on load, and inference on sample mode, BC transcoding, and now also inference on feedback. And I will talk briefly about each of these modes. To give you some more background on NTC in general, just some key facts here that NTC is designed to operate on texture sets, which have up to 16 channels at once. Texture sets such as like PBR textures for one material, including things like base color, roughness, metalness, etc. And it works best if the channels are correlated, similar to BC compression, which also assumes that the channels are correlated. NTC has very widely adjustable compression rate, ranging from 1/32 to 20 bits per pixel per channel, depending on the number of channels. You can adjust, and depending on the content, of course, you can adjust it in a very wide range of compression ratios. Like if you have a very simple material, you can spend less data on it. If it's more complex, then you can spend more data on it and get higher quality. NTC works by training a very small neural network for each material. Basically, in this case, compression into NTC is training, and vice versa. There's no like pre-trained models. There are no large data sets that we use. Just you take a texture set, you train a network for that, and that's it. There is no hallucinations, nothing like that. And the compressed representation that is produced by NTC is it's a combination of 2 things: the latent grid or latent tensor, actually multiple of them, but concept is the same. It's basically just a tensor of parameters that has a smaller size than the original textures. And the network waits for decompressing those tensors back into the original colors, and that's very small, like 12 kilobytes. So the basics of the NTC algorithm are represented on this picture from the paper. I will go into a little bit more detail on the next slide, but the general idea here is that when we do decompression from NTC, inference, we start from that latent grid or feature grid, the same thing, and we have the UV position that we want to decompress for. Like we know where we want the texels that we infer to be located. So we sample the feature grid on that location. We get 2 feature vectors, one high res, one low res. We concatenate them and come up with the input vector for the MLB, for the network, which is the middle here, also combined with some positional encoding to help the network reconstruct higher frequency details. We evaluate the network, and the network produces scaled and biased output texture colors. So, and for compression, we kind of do that and then backpropagate and do it again. So how does the NTC training process work in a little bit more detail? Let's say we have this MIP chain with some leaf texture. And on every training iteration, we start by picking a tile of pixels here, a tile of 32 by 1 pixel, which corresponds to the size of the warp or wavefront on NVIDIA GPUs. And the probability of a particular MIP level being selected here is proportional to the area of MIP level, so that we get more sampling on the larger MIPs. So we have the position of a single pixel, single texel in that tile that we have selected. And we translate it into the UV space, which maps into a position in the feature or latent grids. Then we sample the feature grid and either interpolate the features from the 4 corners or just paste them weighted into the input vector of the MLP, and then evaluate the MLP. We take the colors from the original texture, compute the difference between the original colors and what the MLP has predicted. That generates gradients. We feed back those gradients through the network back into the input vector, back through the interpolation math, and into the feature grid. And then the network weights and the features are optimized. Well, adjusted using the Adam optimizer, and then rinse and repeat until the error is small enough. That process may sound quite expensive, but it's actually been pretty well optimized. So the entire process of NTC is like most of what I showed on the previous slide, the image sampling, the feature sampling, and network evaluation, forward evaluation, error, and backprop, that's all fused into a single kernel, into a single shader. And that the result is that there are no memory road trips, which like we don't load the data excessively from video memory, we don't store it excessively there. And that means the performance is actually pretty good. So the paper, originally the paper that I showed, it quoted something like 10x difference between the PyTorch implementation and the CUDA one. But since the paper, there has been some optimizations, and the CUDA performance is now 25 to 30 times better than the paper, which is 2 orders of magnitude better than PyTorch. And the result is that we can take a single texture set and train the network and latents for it in something like 10 to 30 seconds, depending on the texture size and the quality. I mean, on 4090, yes, of course, and on slower GPUs it will take longer. And this speed up has been achieved by just many separate optimizations. Like there is no single breakthrough that allowed us to get 30 times faster. Now, once we have trained the network, we can use it in the runtime in a renderer. And there are, like I said, there are multiple modes. The first one that was originally described in the paper, or true neural shading mode, it's when we upload the feature grid or the latents onto the GPU and sample the feature grid and do the NTC evaluation for every texture sample that we need for the render. Like instead of sampling the original textures, we take those features and do all that math with the MLP. That's obviously quite expensive. How much it slows down the render, that depends on the complexity of the rendering shaders. Like if it's a forward pass or gbuffer fill pass, it's probably almost negligible, or not negligible, but acceptable. For something very complex like a path tracer, the cost of integrating NTC on sample can be significant. We're working on that, but currently it's not ideal. Although, yeah, like I said, using it in the forward or gbuffer passes is perfectly fine. And another kind of drawback of NTC on sample is that we only predict, like the network only infers one texel unfiltered. So in order to get texture filtering, we have to apply stochastic texture filtering on or STF that jitters the position of the texel that we are inferring. Like if we do an anisotropic sampling, it will be somewhere inside the anisotropic ellipse, and over time it will integrate into the right answer. Inference on load is the compatibility mode, sort of, where instead of doing the inference on each sample, we take the texture set and decompress it when we load it into the game or into the map. So obviously that can be pretty optimized. It doesn't depend on the complexity of the renderer at all. It just modifies how the assets are loaded. So we take the NTC data, decompress it, and then transcode into BC. Whichever BC formats you need for the textures. Like you can use different formats for different subsets of the texture set, like BC7 for base color, for example, and BC5 for metal rough. The transcoding is actually pretty fast, and there is a chart on the right that shows the performance of NTC inference and load on various GPUs with and without cooperative vectors. And with CoopVec, it can be something like 12 gigapixels per second, meaning that you can decompress an entire 4K texture set in like less than a millisecond, actually. And there are you can do many texture transcodes per millisecond, per second, of course. Then the transcoding to BC, that is part of inference and load, it's also very well optimized, and we ship a set of BC encoding kernels with libntc. It's not slow anymore. I mean, if you compare it to offline tools, for example, NVIDIA and NVIDIA texture tools, the NTC implementation is much faster, like orders of magnitude faster. And again, the performance of NTC of BC encoding provided by the library, it's on the order of, again, gigapixels per second. and with some optimizations for BC7, it can also be 10x faster than without them. Optimizations that are specific for like NTC transcoding, there are some interesting things there. And the quality is actually very comparable to what we get from NVIDIA texture tools. And the third mode, like I said, it's inference on feedback. And the idea here is that we integrate NTC, kind of NTC on load 0.5. We integrate it into a virtual texture streaming system. Sort of, if you have a lot of high-resolution textures in the game, you can subdivide them into tiles and only decompress the tiles that you need for a given frame or for a given view. Normally, games use like various heuristics, like how far an object is from a camera or something like that. What we have done here for the sample application, for NTC renderer sample, we are using sampler feedback, which is a relatively new feature in DX12. And we render the frame using sampler feedback, which records the pixels, or rather the pages of the virtual textures that we need to render this particular view. It can be done in the forward pass, it can be done in the path tracer, and obviously a path tracer will generate more samples and will need more texture pages. So we read that feedback after a frame is done, and for the next frame we prepare the pages that pages that are necessary to render a similar view. So there is also a little library in SDK that we recently released called RTX TS for texture streaming, and that SDK handles the logic for managing the tiles of textures that should be decoded and uploaded on the current frame, like manages the occupancy of the virtual textures and so on. So that logic drives which tiles we decompress from NTC and transcode to BC, and the NTC library supports tiled transcoding. So the benefits of this approach are pretty clear, that we don't have much changes to the renderers shaders, like you don't have to do inference on sample, but at the same time you have relatively small memory consumption because of the virtual texturing, and the transcoding is also pretty fast because it happens outside of the main shader, so it doesn't compete with the main renderer for resources like registers. And also, of course, since you have the virtual textures stored with traditional formats like BC, you get hardware filtering, and there is no need for STF in this mode. A few words about the quality of neural texture compression. There are many factors that affect the quality and the compression ratios. Obviously, the big one is the contents of the textures. Like if you have a lot of of small details in the texture set, that's more difficult to compress, so you need more bits to get the same good quality from the texture than if the texture is simple. And there are a few parameters that that NTC library has that control the compression in more detail, like the size of the latent grid, the count of features, etc. But mostly they are auto-determined when you set bits per pixel value. It's all automated in the library. And on the right here, it's a plot of the PSNR or error for 5 materials versus bits per pixel. So like you can see that the curves are mostly monotonic. Like when you increase the number of bits per pixel, you get higher quality of compression. And the BC points here on the lower right, they just indicate that we can get much better quality at the same bit rates as BC, or we can get much lower bit rate with the same quality as BC. And a few other training parameters that affect the image quality or output are the step count, with about 100 to 200 training steps being enough in most cases, which, like I said, translates to something like 20 seconds of training on a 4090. Batch size and random seeded and a few other minor parameters, but mostly it's the bits per pixel and texture contents that affect the quality. And yeah, and here I wanted to show a small demo. Hope it works well. Yeah, this is the NTC Explorer app that I mentioned earlier. I have a texture set, like a material loaded here. It has multiple channels like color, displacement, normals, etc. And it can just use these textures as an input to a very simple renderer that just shows a plane. Now, let's try to compress this. I'll crank down the compression parameters to show the difference. This is the lowest possible setting of 0.5 bits per pixel, and I will reduce the training steps to like 50,000, I think, or 30,000 to make it quicker, because it's a laptop and not a full 3090, or not a full 4090. So this is how training looks live, and 30,000 steps are done. So I can zoom in, I can compare input with output. So you can see the output on the right, it's quite noticeably blurrier than the input because I used a very low compression rate, very low bit rate. Now let's crank it up a bit more to 4 bits per pixel and compress again. Takes a few seconds. And it's much better. So input on the left, output on the right. And actually I can also take the older run, drag it here, and it will show me the difference between two versions of the compression. And actually the same thing, including the live training display, works in the 3D view. So you can see how, for example, how compression settings affect the normal mapping quality or roughness quality, which tends to be quite important for the look. So that's the NTC Explorer. And that's mostly what I had to say. If you're interested in some additional information about NTC, you can take a look at the RTX NTC SDK on GitHub. It's public. It's been that way for about a month. And we have recently released an update that includes the inference on feedback mode. There is also a version of my talk here that I gave earlier in February at Vulcanized, which is a bit more detailed. And that's it for my part.
Hi, I'm Sean Hargreaves. I manage the Direct3D team at Microsoft. And I'm going to just wrap this talk up by introducing a bit of kind of the last piece of the puzzle of what makes these techniques concrete. Hopefully what you've just heard has got you all excited to go off and try training some shaders to do neural shading, to turn some materials into little MLP models, to neural compress your textures. But yeah, the obvious question is, like, how do you ship that? Once you have a great inference model, how are you going to run that at scale across a whole bunch of different GPUs in the marketplace as part of your retail game? And the way to do that is the Cooperative Vectors feature, which Microsoft is announcing this week at GDC. We've been working closely with NVIDIA for a while and other hardware partners to add support for this kind of thing to DirectX. So this is coming to HLSL Shader Model 6.9, which is an upcoming release, as a new industry standard way to implement this kind of neural shading technique. Fundamentally, the problem that we're going after solving with this is, for a while now, there's been dedicated silicon capabilities in GPUs, things like tensor cores, but those have been a black box. That things like DLSS are implemented using this hardware, but you can't reach inside that and write your own shaders to run on that hardware. Well, now you can. We have the support in Shader Model 6.9. We have new Direct3D 12 APIs coming, which will be in charge of uploading the tensor matrices to the optimal format inside GPU buffers. This is going to ship with first-class support in the PIX GPU debugging tool. So what are we adding in detail? We're extending HLSL to support vector and matrix types larger than 4 elements, which is obviously necessary for doing kind of larger tensors. We're adding new specialized vector matrix acceleration hardware operations. So there will be support for vector matrix multiply add, outer product and accumulate, and reduce and accumulate operations. And these are the fundamental building blocks that you need to implement this kind of neural technique in your shaders, both for inference and for training. These are the building blocks of linear algebra, and a lot of machine learning is just fancy terminology for linear algebra. So once you can do things with matrices, you can do anything. These new operations work from any shader stage. That's the part that makes them cooperative. They're most efficient if control flow is uniform and a whole bunch of threads can cooperate on working on one matrix together, but they don't have to be. And that's what makes the kind of inference on sample type technique possible, that you can do inference in a pixel shader, which might be uniform if the GPU is able to arrange that, but often won't be. To learn more about it, I have a link to the current specification here, which has all the gory details of how things work, what formats are supported, what the APIs are going to look like, that kind of thing. Your final question is about availability. When can you get this? And the answer is not quite yet. We are announcing it at GDC this week. we are working towards a developer preview, which is going to come in late April. That is going to be limited to developer mode. So you can't ship a game using that preview, but you can start implementing stuff, build it into your engines. And then we're working towards a retail release by the end of this year. To get this, you will need an updated shader compiler, an updated D3D12 Agility SDK, and an updated driver. We did another talk about this technology on Monday, which is now in the past if you're paying attention. So you'll be able to find a recording of that talk if you weren't able to attend it in the GDC vault after the conference is over. And the most important thing to know is where to go to track for announcements. This link is to our developer blog. We'll be posting both when the preview and the final retail release are available. And that is everything I had to talk about. So we have, I think, probably about 10 minutes left to take some questions. Thank you, everyone. If anybody has questions about any of this, please come up to the microphone, speak into the mic, and any of us will do our best to answer them.
That's it. Yeah. That's it. It was almost side made me like that. That's good expansion. I had rather.
You answered it all already.
I have a question.
Great.
So what's the most common or data type you guys see during the training and the inference process? It will be the using the same maybe floating point system or floating point 8 for both training and the inference, or you'll be different?
One more fun place of cap for months. So yes, it's on. Quite close.
Could you repeat, please?
What?
Could you repeat, please, your question to the mic?
Yeah. So what's the precision is used in the training and the inference process for the neural shading implementation? Is a floating point system or floating point A or even integer?
Okay, so question is what resolution of floating point we use in training, right? Mm-hmm. So we use mixed precision. Obviously, cooperative vector implemented the way that less precision you have, calculate with the more performance you get. So you always want to use lowest one, but it's not always possible, so training can be unstable. So we came up with a mixed precision implementation where training is completely in floating point 16 bits, and optimization use mixed, so it takes calculated derivatives from training step in 16-bit floating point format, and keep a copy of that in 32 bits to continue that optimization process. So that is kind of optimal configuration we found for that.
So is the new IP4 data type support in cooperative vector for the inference?
Yes.
Or do you guys see there'll be like future support?
Don't know.
Maybe.
Yeah, my mic's.
Oh.
So FP4 is currently not supported by cooperative vector features. The lowest format that we have is FP8 or int8. And I wanted to add that for neural texture compression, training happens in FP16, while inference happens in either FP8, E4M3, or FP6, or int8.
Okay, thank you.
For neural shading, do you do any transformations to the input data, like mobilize to tangent space or do anything to make it easier for the neural network?
So basically everything happens in if you're talking about training process itself. So it happens in computation, in compute shader. And actually the way we generate training data, we use a random generator in every instance. So it's special form of random generator that has thread ID as an input, so every thread has its own sequence of random numbers. And we generate those vectors in the way that it's most easy for us. So basically, it's in tangent space where normal vector is along the z-axis, and we generate all additional, I don't remember, probably 2 additional vectors just in a polar coordinate system in the way that it would not produce like negative dot products because it's obviously black, so we don't want to train neural network for those values.
Okay, thank you.
Good.
I'm really interested in the neural texture compression. Actually, we have tried it in our project. The quality is impressive, but the key point to our project or the real-time game engine is the performance of inference. Even though we inference on the background and then compress by BC7 and then sample, but the inference step is still too low. It costs about 10 milliseconds to 20 milliseconds per 4K texture. Do you have any suggestion for us to do some further work to optimize the inference time?
That depends on which GPU and you are working with, and if you were using cooperative vectors.
From 1416 to 1490, the time cost from 10 milliseconds to 20 milliseconds, and the target of our game is 1016 or lower.
Yeah, for the 40 series, it should be faster than 10 milliseconds per 4K texture. If cooperative vector is enabled, it's more like 1.3, I think, on 4090. 4060, I guess maybe like 5. I don't have any numbers. But yeah, 10 sounds a bit too expensive. You can try to do inference on feedback or something like that when you transcode partial tiles. Like when you transcode tiles of textures and distribute transcoding of one texture into multiple frames.
All right. It sounds like partial the texture into several tiles, like virtual texture, right?
Well, not necessarily virtual. If you don't have a virtual texturing system, it would be easier to just
I get it.
Yeah.
I get it. I still have a question. We have tried use the MIP map of high level, such as the 512 MIP, but the time still the same with the original MIP. I don't know why.
No, that doesn't sound right. Maybe you had some integration bug, but the time there is definitely proportional to the area in pixels.
I mean, we stripped the higher MIP for one texture.
Yeah.
But the time.
But like I said, if you
keep the same.
If you decompress and then recompress the like the MIP2, for example, it should take much less time than MIP0 because the MIP2 is much smaller, and that's what we saw in testing. Like I said, probably there is something wrong with your implementation there.
All right, so must something get wrong. So
yeah,
that solution should be work, right?
Yes, smaller MIPs should definitely decompress faster.
All right, I know. And the last question is, I saw the NTC is supported by the ASTC and Vulkan, so it should be run on mobile, right?
On mobile we haven't tested. In principle, it should work, but the decompression could probably be too slow for a mobile.
All right. Okay, thank you.
I think we don't really have much more time for questions right now.
Yeah.
Thank you, though. We should be available somewhere outside.